Hello, I'm Laura Lewis. Welcome to Star Life Cycle class today. I'm just going to share my screen with you. Start present. I might be muted for the first few seconds there, I think. Okay, so this is Star Life Cycle. So this is part of the GCSE physics syllabus for all the exam boards we're going to look at. So some of you may know it from year 9. You may have read things about it, but we're going to start right at the beginning. Okay, with the learning aims. So today's sort of learning aims for this class are an understanding of how stars are born in nebulae. That's the plural of nebula, nebulae. It's a Latin word. It means cloud. It's quite fitting for it, as you find out. An overview of the life cycles of stars with different masses. So each star will have a different life cycle according to its mass. And the fate of various stars and the formation of black holes. Ooh, okay, interesting there. Okay, so stars could form a black hole, which we'll get on to talk about. So we'll just next slide here. This is one of my favourite subjects, by the way. My degree is in astrophysics. So this is one of the prettiest diagrams that you can see in science, in my opinion. The Hertzsprung-Russell diagram, named after two people. Okay, Hertzsprung and Russell. So it actually shows stars of different masses and temperature. So it's all about taking all the stars in the sky that we can see off with telescopes and putting them on the graph. Okay, it's quite an interesting idea. So you've got surface temperature in Kelvin. Okay, and so Kelvin is like Celsius, but you just convert. So zero Kelvin would be minus 273. So if you get Celsius and add 273 to it, you get Kelvin. So on these scales, it's actually not significant because there's tens of thousands of degrees Kelvin. So this is increasing. So it's actually backwards, this graph. So actually increasing temperature is this end. So the darker blue is higher temperature and the red is lower temperature. Okay, so 30,000 degrees. So some of the hottest stars are 30,000 degrees Kelvin or Celsius, and the cooler are under 3,000. So they're quite cold for a star. Okay, you can see our sun is towards the lower mass of stars. Okay, it's kind of average, but it's towards the lower mass. It will be classified as a G2. So there's these names O, B, A, F, G, K, M. Okay, these are classifications of stars. It'll be classified as a G2 yellow dwarf because it's yellow. It's actually quite a small star, so we call it a dwarf star. Other stars in the sky you may recognise, you may not recognise, depending on. I'm involved in astronomy. I'm going to move myself down over here to have a look at the graph. Deneb is in the constellation Cygnus. So these stars you can see in the sky. Rigel is in Orion. That's quite a familiar constellation for the winter time, people in the northern hemisphere. Betelgeuse also in Orion. Antares, that's in the constellation Scorpio. Might see it, might not. Vega, Sirius. Sirius is the brightest star in the sky to us. As you can see here, it's not actually a particularly big star, it's just because it's quite close. Okay, so some stars are quite small, but they're quite close to us. Well, they're still several light years, but they're closer than some of these bigger stars to us in the sky. So these are all stars. So you can see a nice colour range here, going from blue to white to red. So you think why it's to do with the surface temperatures, why different colours. So the bluer the star, the hotter it is, and the redder the star, the cooler it is. Maybe could not be common sense to people watching, but that's actually the truth there. Okay, star formations. So let's start at the beginning here. What makes all these different stars? So if they form stars forming nebulae. So this is the nebula in Orion. It's quite creatively called the Orion Nebula. You can see little white dots. These are actually stars forming in it. So how does that happen? So nebulae are huge. Okay, they're bigger than our solar system. So this is bigger than our solar system. So all the planets would fit inside this. It is that big. So parts of the nebula collapse due to gravitational attraction. So yeah, the nebula actually sort of collapses down because gravity just attracts it because there's so much mass there. Gravity attracts it together to form something called a protostar. So that's just a big ball of gas at that present. It's just a big ball of gas. It does emit light, but it doesn't. It's not quite a star yet. It's still called a protostar because there's energy conversion going on between gravitational potential energy, that's gravity, and kinetics. It's just all the matter pulling together that lights up the gas, because actually it creates a lot of friction, lights it up. So there's still anything that hasn't begun nuclear fusion. It's called a protostar. Okay, so it's shining, but it's not using nuclear fusion yet, which we'll get on to talk about. So yeah, they can form at different masses. So within the nebula, you can get different masses of stars forming. So some are smaller and cooler than our sun. So we've got these little red dwarfs here. I remember from the Hertzsprung-Russell diagram. Some just form very small, and some are much larger. So some of the stars in the sky are much bigger. They actually look much bigger, but there's a limit on how big a star can be. They're probably only about 30, so it's based on physical equations, only about 30 times the mass of our sun. So you may see a really big star, but its mass, as the biggest stars ever found, possibly nearing about 30, 40 times mass of our sun. Never say there isn't others out there that are bigger, but they are much bigger in radius, okay, but they're not how much more massive as you think they are, okay, because there's physical limitations on how big a star can be. Basically, part of it just doesn't pull together enough. So stars are considered to be in the main sequence once nuclear fusion has begun in their core. That's a very key point here, is that they're on the main sequence, like the main part of their life, once nuclear fusion has occurred in their cores. Okay, so once all the gas is hot enough and compressed enough in the core of the stars, nuclear fusion starts. So we can detail that next. So what nuclear fusion is. So the sun is a main sequence star. It's producing a lot of energy, a lot of light. So all main sequence stars, including our sun, fuse hydrogen in their core. So you've got an equation here. So hydrogen and hydrogen fuse together, stick together to form helium and release a lot of energy. And most of that energy is light, in the form of light. Okay, so you've probably heard different types of energy. Most of the energy is in the form of light. So we experience that as like the sun shining in the sky. It's actually a very sunny day today here. You can tell my camera, it's very sunny. So the sun is always fusing hydrogen in its core to form helium. So yeah, people have attempted nuclear fusion on Earth, and it's a clean process. It doesn't produce any nuclear waste, but it's been achieved. I went to a place in Oxfordshire called Cullen, where it's been achieved, but we haven't what's known as break-even. We haven't had break-even fusion yet, which means we haven't actually got more energy out than we put in. So we're trying to make it like a nice clean source, like the sun has, but we haven't achieved it quite yet. Okay, but yeah, all main sequence stars have nuclear fusion, this process occurring in their core. So right in the middle it occurs. We don't see it on its surface. That's just as light radiating out. But it occurs in the core, right in the middle of the sun, where we can't see. Okay, so at some point the hydrogen will run out. Okay, so it's big, but it's still finite, so it's not infinite supply of hydrogen in that core. So a main sequence star reaches the end of its life due to that hydrogen running out. Once it's fused it all into helium, some stars can fuse heavier elements than that. They can fuse up to iron, which we'll talk about a bit later in the video. But our sun will probably fuse elements up to carbon, okay, because our sun's quite small. So depending on the original size, the star will become a red giant or red supergiant, depending on how big the original star is. So the sun will become a red giant in about 5 billion years. So we've got time. So okay, you've got time to do your homework. 5 billion years I have to worry about today. It will destroy Mercury and Venus in the process. Yeah, it will. It would expand. So yeah, so the actual star expands. It kind of loses its layers slowly in the process, become a red dwarf giant, and it will actually destroy the inner planets in the process. I think Earth will just be okay, but be very hot. So yeah, after becoming a red giant or supergiant, so you've got this stage, you kind of got to this point. The path of stellar evolution diverges, so it splits into two. So if a star is similar in size to the sun, it will lose its outer layer. So it's kind of like a very sedate death for the sun. It doesn't blow up or anything. over time, it just loses its outer layers in a process that's called becoming a planetary nebula. It's nothing to do with planets, actually, very badly named. All it is the people that first discovered it thought it looked like a planet through a telescope. There's nothing to do with planets there. Okay, and there's no explosion, it just loses its outer layers. And the core is left. So the core, which used to undergo nuclear fusion, doesn't anymore. It's just left as a white dwarf, and it will just slowly cool down over time, fade. I know, I think quite a sad end for the sun, isn't it? But it won't happen for a very, very long time. For 5 billion years, it will happen. So that's the sun. So similar size stars to the sun, quite a sort of gentle end to them, and they won't explode. But much more interestingly, in a way, massive stars. So a minimum of about 10 times bigger than the sun, so not considerably that much bigger than the sun, will end their lives in a supernova explosion. So what happens is that the core of the star fuses elements all the way up to iron, and once it gets to iron, it can't make any more energy. So the core collapses on itself, okay, because there's no radiation pressure pushing the outer layers out, because when it undergoes nuclear fusion, it actually creates a pressure. So the core, the outer layers just come in, they actually bounce off the iron core, literally bounce off the iron core, and this happens in a few seconds, okay? Remember, the star's been living for billions of years, and this process happens in a few seconds. And it rebounds so violently, we see it as a supernova. So this is a star, the star's right in the middle there, has become, has exploded in a supernova. And it's sort of a supernova remnant. So remnants means something's left. Okay. So yeah, they can be bright. This is a supernova in a galaxy, a different galaxy. So that's just one star. That's the whole galaxy, and that's just one star. So it actually can be as bright as the whole galaxy for a number of weeks. So much like energy is released, so much thermal energy is released. It can actually be as bright as the whole galaxy for a few weeks. And what is left behind after that explosion, like the core of the star, it can be a neutron star or a black hole. Okay, so that's an interesting thing. So I'll move myself down for a minute, sort of blocking the picture there. Okay, a neutron star. So these are very interesting things. So between 10 and 25 solar masses would create a neutron star. So they're very bizarre objects. They're one of my favourite objects in the universe to study. So the bizarre objects, yeah, they are truly bizarre. They emit deadly radiation, so no life would be found. Any planets that manage to survive that supernova, that would be like the final end for any life there is. So I've got a nice sort of artist impression here of a radiation beam. It's actually what happens. A radiation beam comes out of the poles, okay, of the neutron star. So yeah, huge like gamma radiation comes out of it. It links to other parts of physics there. You have huge gamma radiation fields around this. They are the most powerful magnetic fields in the universe. So they actually obviously also be dangerous because magnetic fields would be strong enough to rip apart any kind of spacecraft that went near there as well. It would just literally rip it apart. So you don't worry about these. They're many, many hundreds of light years away. You'll never ever encounter one. You don't have to be worried about it. It's very interesting. They're the densest objects in the universe as well because they've got a solid surface. It's a star with a solid surface. That's even more bizarre. They're a star with a solid surface. That if you manage to get a sample of one, which again would be impossible because you wouldn't have to get anywhere near it. So a spoonful, just sort of like a little sugar cube, would weigh thousands of tons because so much matter of that original star, when it collapsed before the supernova, it kind of all smashed all the matter together to form a very, very dense object, so the neutron star. So some of them rotate, and they're called pulsars. So some of them rotate and they're called pulsars. So that's an interesting thing. They are the most accurate objects in the universe. They spin around at several times a millisecond. Some of them spin faster than that, and actually you can use them as to measure time. They're so accurate. So it's a thing worth looking at with neutron stars. So black holes. Okay, stars that are over 25 times the mass of the sun. So you may have heard, obviously, people observing a black hole. There's different types of black hole. This one is a stellar mass black hole, so it's a black hole that's formed from a star collapsing. Okay, there's other ones that form in the middle of galaxies. Is the one that was discovered a year or two ago. Now was the one that was an object. It was one in the middle of a galaxy. That's a bit of a different type of black hole. That's a galactic black hole. This is a stellar mass black hole. So yeah, stars that are over 25 times the mass of the sun will leave a black hole after the supernova. Yeah, it's a bit misleading actually because they're three-dimensional objects. This is kind of quite a good impression of one. Obviously, again, artist creation here, because they're actually three-dimensional. Okay, they're not the word hole. You always think of a hole in a piece of paper, don't you? You think it's two-dimensional, but they're not. They're three-dimensional. So light would be bent around them as well. Okay, so to create this sort of weird optical effect if you went near one. So they appear black as their escape velocity. So the speed you need to go out to get away from that body is actually greater than the speed of light. So light cannot escape its surface. Okay, so that's why they appear black, is that any light falling on it can't escape its surface. Nothing around the black hole isn't black there, however. As you can see, this is actually a very, very accurate drawing. Is that around the black hole you'd see an accretion disk where lots of gas is being sucked into it and actually emitting radiation. So it's only like this bit in the middle that's black. So you would get an accretion disk around it, which isn't. So probably the most thing people find most interesting about black holes is, do they lead to another part of the universe or another universe? So no one knows that. Okay, but it's possible. It's possible. Maybe if people find out in future, maybe people watch the video might find out that it's unknown whether black holes lead to another part of the universe. So we don't know where they actually go. Okay, no one's ever found out where they go. Because what would happen if you approach this, again, don't need to worry about it. These are many, many hundreds of light years away. You'll never encounter one. If you approached a black hole, if you approached a black hole in a spaceship, it would the gravitational effect would be so great, it would rip it apart again. These quite interesting objects, but you'd never be able to get near one. Not with our current technology. Never be able to get near a black hole. But yeah, again, they're very interesting objects. So only the most massive stars will go for a supernova and will end up as a black hole. Only the most massive stars in the universe. Okay, so I'm just going to go over what we've been learning about. Go right back to the beginning. A nice animation there. It slows the computer down a bit, so I don't tend to use too many. So yeah, understanding how stars are born in nebulae. So this was that slide about gravitational collapse causes the nebula, the gas and nebula to collapse and become together to form the protostars, and they shine by gravitational potential energy converting energy to kinetic and then to light energy. So nice little energy conversion diagram you could draw for that. Overview of life cycles of stars with different masses. So yeah, if we want to sort of look back, so different life cycles of stars. So the average star, so sun-like star, red giant, Pantry, Nebula, white dwarf. Okay, and fading away over time. A massive star, so over about 8 to 10, so 10 times mass of the sun. Red supergiant, a slightly different, but it just gets bigger than the red giant. Supernova, okay, that's a very different thing. Isn't only the massive stars will go to supernova, the sun will not supernova. And then you'll be left with a neutron star or black hole, depending on the mass. So 10 and 25, you get a neutron star. Again, future research, these parameters may change a bit. That's always interesting how this is the forefront of research. Over 25, we think at the moment you'll get a black hole. Okay, so that's a very interesting field of light. So yeah, it's good to go over the main points again and look at nuclear fusion. Remember, the main sequence is defined by stars actually undergo nuclear fusion in their cores. Okay, so I'm going to run back a video and make notes and things when you watch the recording. Okay, so and this is actually a very good overview of stars at different points in their life cycle. So a star actually could start on the main sequence like our sun. I'm going to move myself from it there. The sun, and then actually during its life, it can be at different points on this diagram. So the sun would move up here through the giants when it gets older, and then loses its layers, goes to be a white dwarf. Okay, so stars aren't stuck on this. Okay, they can move throughout their life. So you may get a diagram, Hertzsprung-Russell diagram. So where's the sun going to travel to during its life? Okay, so yeah, up to the giants, red giant, and then it'll go back. Then it'll go down to being a white dwarf. Okay, or supermassive star will become a supergiant. Okay, but it wouldn't be so. Neutron stars and black holes are not represented here. Okay, so yeah, it's a good overview. We've looked at how stars are born, nebulae, overview of the life cycle with different masses, so you can go over that, and the fate, so the eventual would happen eventually, that means fate, of various stars and the formation of black holes. Okay, yeah, so the black hole was formed after the supernova. Okay, so it collapsed on itself. The reason why, it's a bit of an extra bit at the end here, I kind of thought something. So the more mass the star has, the more it will collapse, basically. So neutron star is the densest form of matter, so all the mass is collapsed. If it collapses any further than that, it actually starts kind of breaking a few laws of known physics, okay, and become a black hole. But these, you won't be asked exactly what laws it's breaking, okay. Just obviously the most massive stars become black holes, because again, right at the forefront of physics research is the black holes. Okay, so I hope you found that interesting. I liked presenting it. I like talking about stars. Thank you for joining the class today. I'm going to stop recording. There. Thank you for joining the class, and hope to see you in a different class soon.